Hello, so in today's video, we're going to look at sketching quartic functions. So basically, functions which are polynomials of degree 4. So in other words, the biggest power of x that we have is a power of 4. So that's what quartic functions are. So we're just going to go through briefly two examples. We don't need to worry about sketching advanced quartic functions. We only need to worry about sketching quartic functions where we can actually factorize the quartic into linear factors, as we'll see in these two examples here. So we won't really get examples much harder than these two examples here that we need to worry about. So yeah, let's start with the first example here. So sketch this graph here. Actually, before that, I'm just going to go through briefly what quartic functions usually look like. So usually, yeah, if you have like a quartic, y equals a times x to the power 4 plus bx cubed plus cx squared plus dx plus e. So these are quartics. So if a is positive, they will normally have this kind of shape here, kind of like a W shape like that. So we get 4 solutions. So 1, 2, 3, 4. So in general, in many cases, these graphs will have 4, or these functions will have 4 solutions, or 4 roots, I should say. And then when the a constant or coefficient is negative, usually they look like this instead. So this upside down shape instead. So again, normally 4 solutions, but as we saw with these cubics, and as we know with quadratics too, we can sometimes get repeated roots or even no roots as well. It just depends on how we can factorize our quartic. So yeah, if we go back to the example then, so example number 1, this one here, yeah, let's try this one. So the key thing we want to do is always with these kind of graph sketches is see if we can factorize it. And again, with these questions in A-level maths, we will be able to factorize them. So factorizing this first quadratic term here, x squared plus 5x plus 6, we can factorize that like this. So x plus 3 and x plus 2 there. 2 times 3 is 6 and 3 plus 2 is 5. So that's how we factorize that. And a similar story with this quadratic factor here. So factorizing the x squared plus 4x plus 3, we would get an x plus 3 in there and an x plus 1 in there. So we can actually write this quartic like this instead. So x plus 3 squared, due to the fact we have 2x plus 3 factors, multiplied by x plus 2 and times by x plus 1. So that's what we have. So how are we going to sketch this? So the key thing to realize again with this sketch is we're actually going to have just 3 real solutions, but one of those solutions is repeated. So the root from this, given from this term here, we get a root of x minus 3. So a root of x minus 3 is a root, but this is a repeated root. So if we remember from the last video, where we looked at cubics, and also the same story of quadratics too, when you have a linear factor squared, this gives rise to a repeated root, and it's a root which just touches the x-axis rather than passes through the x-axis. And with these 2 roots here that come from these factors here, so we get a root of x equals minus 2 and a root of x equals minus 1. So this is just these are just simple roots. Since there's no multiplicity, we're not multiplying this factor by itself again. So this is just a simple root. And again, this is a simple root here. So then what will our sketch look like? So we try and draw a sketch here. Our y-axis there, our x-axis there. So we've got a repeated root at x equals minus 3. Let's just put minus 3 there. So that's minus 3, that's minus 2, and that's minus 1. So it's a positive quartic because the a value is positive. The a value is just going to be positive 1, because when we expand the brackets, we would get an x to the power 4 as our x to the power 4 term. So this is greater than 0. So it's going to be our usual shape. So our usual normal positive quartic shape is this kind of W shape that I mentioned before. So it's going to be that kind of shape. But what will it look like? So it's going to start from going up, and then because it's got a repeated root at x minus 3, it will not pass through x minus 3. It will just touch x minus 3. It will then go up again, but now it will pass through x minus 2 because this is just a simple root. There's no multiplicity here other than just 1. So then again, it's going to go through -1. It's going to actually go through this root here because, again, this is a simple root. The multiplicity is 1, and then it's going to pass through up. Sorry, let me try and do this better. Something like this. So that's what our sketch would look like. And what would this y-intercept be? Well, it's just going to be the product of these two numbers there. So 6 times 3 is 18. So you're going to have a y-intercept at 18. So yeah, that's what this sketch would look like. Again, a repeated root of -3, and then these two simple roots at -2 and -1. Okay, great. Let's go to the next example. So this one here, x minus 4 x to the power 4 minus 81. Again, we could factorize this because this is essentially a difference of two squares. So using our difference of two squares factorization, let me just make a note of this, difference of two squares. So we get x plus 9 and x squared plus 9 and x squared subtract 9. And again, we can actually factorize even further. So x squared plus 9 multiplied by x plus 3 times by x minus 3, because, again, using the difference of two squares, we can use the same approach to factorize this even further there. So we want to sketch this graph. Again, we're going to have a root here of -3, so x equals -3 is a root, and it's going to be, again, a simple root because we've got a multiplicity of just 1, simple root. And this factor here will give rise to a root at x equals 3. Again, this is just a simple root. There's no multiplicity here. How about this quadratic term here? I mean, if we let this be equal to 0, x squared plus 9 equals 0, we get x squared is equal to -9. Now, when we take the square root of -9, we don't get a real number. We get a complex number. So we actually get no real roots from here. So no real roots from this factor. So we don't need to worry about any roots from this factor because we get no real roots from that factor. Okay, so what will this graph look like? So it's going to be a symmetrical graph. So similar to how the x squared minus a constant functions, x squared plus constant functions are symmetrical, these quartic functions with just an x to the power 4 minus a constant will be symmetrical. So the graph is going to kind of look something like this. So symmetrical about the y-axis is what I really mean. So the y-axis there, x-axis there. We've got a simple root at -3. I'll just put that there. Another one at 3. So again, the graph is going to have a positive quartic shape because the a value is bigger than 0. As we can see up here, the a value is 1. Let's just make a note of this again. The a value is bigger than 0 because a equals 1. So it's going to have this W shape again rather than this upside down W shape. So that's the key thing to remember. So again, it's going to be a W shape, and it's going to, so this is our smallest root. So it's going to pass through that root again because this is a simple root. The multiplicity is equal to 1. There's no repeated factor here. So it's going to go through straight through like that. And then it's going to, well, we know we've got a y-intercept of -81. Let's actually just put that down there. So -81 is a y-intercept. So you've got a y-intercept of -81, and we've got this other root here of 3. So again, because of the quartic shape, the biggest root we've got is 3. So the biggest root, again, is just going to pass through, as we can see from this diagram there. So we're going to pass through down there. And then, okay, so how will the quartic behave from here? Well, actually very similar to a quadratic shape, though what we'll actually notice is that, let me try and draw this again a little bit neater. So even though it is a quartic, it won't have this kind of W shape. And that's due to the nature of the roots that we have. We only have 2 roots here. And because we know that a graph of x to the power of 4 kind of, again, has this not parabola shape, but kind of that kind of shape. So it kind of looks something like this, with kind of a flat or a flatter minimum point there. It's going to kind of look like a quadratic, but a little bit flatter at this point there, rather than an exact minimum point, a bit more flatter at the bottom down there. And again, you can check this using a graphing software. If you sketch y equals x to the power of 4, you do get somehow a graph that kind of resembles a quadratic, but again, at this point there, we get more of a straight gradient, a horizontal flat gradient there. And again, that's due to the fact that this is actually a repeated root with this example here, because we've got the root here of x equals 4. This is repeated, and we can see that it's actually repeated with a multiplicity of 4, because when you sub in, or when you make this equal to 0, you get a root of x equals 0 with a multiplicity of 4 due to this power of 4 there. So that's kind of the reason why it's flatter at this part here. And it's kind of, again, due to the fact that we have this quadratic factor, but it's not giving us any real roots. It just gives us complex roots. We don't need to, we don't factor that in when we deal with these real sketches of real functions. So yeah, so in general then, quartics do have this W shape, or perhaps this upside down W shape in the case when you've got a negative A constant. But with these ones, with these x to the 4 graphs, when you just add or take away a constant like this one here, they do kind of look just more like a quadratic, however, with a flatter minimum point, with still curved, but a flatter kind of curve at the bottom here. So yeah, that concludes today's video.